For today's lesson, we are simplifying radicals to their exact values. The reason we are going to go over this concept is because it's the last part of the quadratic formula that we haven't seen. So let's look at the quadratic formula. What do you recognize? Hopefully you saw that the discriminant is underneath the square root, b squared minus 4ac. We just used this on last lesson to help us find how many solutions and what type of solutions we would have. The other part that we should have noticed is the opposite of b over 2a is at the front of the quadratic formula. The only part we haven't talked about is the plus or minus the square root. This is a part of the formula because we are solving quadratics, which have to have an x squared term. To solve for the x squared term, you have to do the inverse operation and square root both sides. This gives you plus or minus the square root. So let's start simplifying radicals in today's lesson, because next lesson we are putting it all together and solving quadratics by using the quadratic formula. On today's bell ringer, you reviewed how to make a factor tree or find factors of the given value. That is what we do with simplifying radicals. So one way we can break down 12 is breaking it down to 6 and 2. We also know that 6 breaks down to 3 and 2, and we're going to carry down the other 2 we already had. So if I multiply 3 times 2 times 2, this equals 12. Now for us to be able to take a number out of a square root, it has to appear twice. If we look, the 2 appears twice, meaning I can take the value of 2 and set it outside the radical and leave 3 on the inside because there's nothing I can do with it. Now the shortcuts that I would recommend you guys using is by using a perfect square. We know that quadratics have an x squared term, so that means that there has to be some kind of number that was squared in the quadratic. So another way we could break down 12 is breaking it down to 4 and 3. If we take the square roots of both of these numbers, we know that the square root of 4 is 2. There is no square root of 3, so we just bring it down and make it part of the answer. So either way you do these problems, it will come out to be the right answer. But using perfect squares is going to make it an easier and faster process. So let's go ahead and make a perfect square list. I'm only making the list up to 12, but feel free to take it as far as you want to. If I were to square all these numbers, we would get a list of 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, and 144. This list is going to appear on the bottom of the PowerPoint. I would just make sure that you write this down in your own notebook, especially for the independent practice. So let's look at example 2. To use the perfect square list, you want to start with the highest square root and work your way down. So let's go ahead and start with 363. I try to divide it by 144. It is not possible. But if I divide it by 121, I get the value of 3. So I know 121 times 3 is 363. Take the square root of both of the numbers. We know that the square root of 121 is 11 because we would just take away that square. And the square root of 3, there is no simplification of that, so we just bring it down, and there's our answer. For example 3, same process. So we take 175 and start dividing it by the perfect squares. I know that I don't need to start with 100 because if I double 100, it's already at 200, so there's no reason to double check that one. It's okay if you do. I'm just trying to help you even shorten the process for yourselves. So 175 divided by 81 doesn't work out, nor does 64. If I divide 175 by 49, it still doesn't work. Divide it by 36, it does not. But we know that 25 divides into it 7 times. If we do 25 times 7, it equals 175. Take the square root of both of these numbers. Square root of 25 is 5, and we bring down the radical 7. And there's our answer. So in the quadratic formula, the only thing we will have is a value. In today's practice, we are going to take it a little bit further just to enrich the lesson and show you what you would have to do if you have variables that have exponents. Let's look at example 4. Like I said, it's going to have an integer and a variable with an exponent. Reminder that if there isn't a numerical value for the exponent, it is 1. So let's break down 63, divide it by perfect squares. I'm going to start pretty low for this one. 25 times 2 is 50, so I'm going to go ahead and start with 16. 63 divided by 16 does not work. 63 divided by 9 does. It's 9 and 7. Take the square root of both of those. The only new part here is that we're trying to figure out how many n's I can take out. So n to the third breaks down to n times n times n. I need a pair of it to be able to take out an n. I do have a pair, so I'm going to be able to take out one n with the 3 I'm going to be able to take from the square root of 9. So we would have this square root of 9 equaling 3, but also carrying down the n. So we have a leftover square root of 7 and a leftover n that is going to go back on the inside. So our final answer would be 3n times the square root of 7n. Another way to look at it is you take the exponent and you divide it by the root. The root is 2, so if I do 3 divided by 2, 2 goes into 3 evenly once, so that means I can take out 1n and have a remainder of 1n on the inside. So let's go ahead and look at example 5. So for 512, the highest perfect square that could divide into it from our list is 64. It would be 64 and 8. We will take the square root of both of those, but we're going to go ahead and break down our r's. There are 2. So that means that I can take out both of the r's and just write r on the outside. Plus, if we do 2 divided by 2, we get 1. So we're going to be able to take out 1 r. If we look at 8, it is not a prime number, plus there is a perfect square inside of 8. It's 4, so we could break it down even further to 4 and 2. We're going to go ahead and take the square root of both of those and bring down the square root of 64. There are 2 perfect squares in this problem, so that means that the perfect square that we're taking out of it is larger than 12. Our list only goes to 12 squared, so this is why it's going to double up. So the square root of 64 is 8. The square root of 4 is 2. And we have 1 r that we're taking out. So we would have 8 times 2 times r on the outside. And we'd have the leftover square root of 2. So this simplifies to 16r times the square root of 2. So sometimes the integer we are given will have a larger perfect square than 12. But typically, the perfect square list all the way up to 12 will suffice for the problems that you are given. So example 6, 7, and 8, if you want, you can go ahead and pause and try to do these on your own. If we look at example 6 and break down 32, the highest perfect square that divided into it was 16. 16 times 2 is 32. We would take the square root of both of those. So we're just going to divide out our exponents on these examples. If I look at this x, it has an exponent of 1. So I already know I can't take out any of the x's because there has to be at least 2. So that x is going to stay on the inside. If I look at my y's, there are 5. And if I take 5 divided by 2, that means I can take 2 y's out evenly and have a leftover y. So on the outside, the square root of 16 is 4. Plus the 2 y's I was able to take out from y to the 5th. Left on the inside, we're going to have a 2 and the x and the leftover y. Our final answer is 4y squared times the radical of 2xy. If you need to write out all of the variables you are given and circle up pairs, you are more than welcome to do so. Example 7. Trying to find the perfect square that divides into 343. We would go all the way to 49. 49 times 7 is 343. We're going to take the square root of both of those numbers. Let's look at our variables. For x to the third, 2 divides into 3 evenly once with one remainder. So I'll have an x I can take out and an x left on the inside. We have 2y's, so that means we're going to be able to take out 1y. And we have 10 z's. So if I do 10 divided by 2, that means I have 5 z's I can take out. So the square root of 49 is 7. The x I could take out, the y I could take out, and the 5 z's I could take out, leaving me with 7 and the x that was left over from dividing the 3 by 2. Hopefully you are seeing that if we are taking the square root and our exponent is odd, then that means we're going to have one left over, which makes sense because odd numbers can't be divided by 2, so we'd have one left over. The evens do divide by 2 evenly, so that's why they all get taken out on the outside. So final answer, 7x, y, z to the fifth times the radical of 7x. Looking at example 8, we have 64, which is a perfect square. So there's no reason to break it down. We can just simply write that 64 goes to 8. My x exponent is even, so that means I will take all the x's out. My y is odd, so that means I'll have one left over. Same thing with my z. So for my x's, I can take 2 out. For my y's, I can take 2 out. And for my z's, I can only take 1 out. Again, all I'm doing is dividing my exponents by 2 and taking that number that it divides evenly on the outside and keeping that as the exponent. And whatever's the remainder goes back on the inside. So for this one, the square root of 64 is 8. We can take out 2 x's, 2 y's, and a z, and have only left over 1 y and a z. So on today's practice, you're going to continue doing this. They progressively get a little bit more complicated with more variables. Take your time, check your answers, but make sure that you are practicing simplifying the radicals because next lesson we will be solving using the quadratic formula, which will have a lot of reducing with the square roots. So go practice away and have a good one.